Alright, this is Math 2510, and this video is going to be over section 2.4 and 2.5, which is looking at infinite limits and limits at infinity. So when we say infinite limits, we're looking at as x goes to either infinity or negative infinity. So x is getting really, really big, and so you're looking at it as going to the right and fall out to the right, or it's getting really, really small, so it's going to the left and fall out to the left. And we look what happens to the function at these times. So we will say as x approaches infinity or approaches negative infinity when we mean infinite limits. So let's look at the function x squared divided by x squared plus 1. And let's graph it. I'm going to graph in Desmos. So f of x equals x squared divided by x squared plus 1. Okay. And we see we have a graph that looks like this. Looks kind of like a bird. Comes down as we go towards 0, comes down to this like hill in a sense. So just a dip right at 0. Okay. Let's get a table. So we'll do table, and we'll put this in as x. We'll put this in as f of x. We can plot some points so we can see that some points on the graph as well. And we're going to want to zoom out some as well with this. We're looking at, let me decide on this. Negative 1,000. 1,000. A step of maybe 100. And the y, we don't want that as big. Negative 5 to 5. See, that looks better. Right, so you can't really see the dip all that much, but we know it does happen. Okay, now, we're more concentrating right now at when we're going to the left and when we're going to the right. We see that it almost becomes like a horizontal line. So let's look at the values. Negative 1,000. We get 0.999. You can fill in that table as we do these. The negative 100. And still 0.9999, but there's some zeros after that. Negative 10. This is 0.99. And we'll do, let's do 1. And we get 0.5. Okay. I'm just going to scroll over this way. Right, so, it's, when we're close to 0, you get a number that's between 0 and 1. 1 is halfway, but as soon as we start, that's a negative 1. As soon as we start increasing x or decreasing x in the negative direction, it jumps up and gets closer and closer to 1. And that's the way it is all the way through. So we would say with this that the limit as x goes to negative infinity of f of x is equal to 1. Even though this number isn't going to actually equal 1 at any point. I mean, if you look at the fraction itself, you have the numerator. The denominator is always the numerator plus 1. So it's always going to be a little bit different, but that number starts to get closer and closer to 1 as you go. And then we can look at the other side. You put in 0 and you get 0. You put in 1, you get 0.5. Put in 100, comes up to 0.99. Put in 1,000, comes up to 0.999999. Alright, so as limit as f of x as x goes to infinity also equals 1 here. Now, there can be a limit on either side of these. They don't have to be equal. Sometimes they won't be. For example, let's zoom out. I should not zoom in right around the center here. Let's adjust this so it's lower. Right. So we can see that. Now let's change the function. So it's going to both go -1. Try. You can see a little different as it goes to the left and as it goes to the right. Here you have an asymptote, but as this way, this goes to 1. On this side, this goes to 1. So, we're looking at for these on the ends and how they go. Right. We did both of these. Limit as x goes to infinity of our function goes to 1 for both of them. Right. So, in general, when we say the limit as x goes to infinity of f of x equals L, this means that the graph of f of x approaches L as you plug in larger and larger values of x. Positive values of x. And when x is going negative infinity, you're plugging in larger and larger values of negative x. Larger in the sense of the numbers are bigger. They're negative, so they're actually really smaller. We can set x equal to 10 to the 6th power, and we're still going to get something that's not exactly equal to 1. It's going to be a long digit with a lot of 9s, some 0s, some more 9s. This isn't equal to 1. We can say it's roughly 1. The limit is going to 1. Alright, so this is how we kind of define the horizontal asymptote. The limit as x goes to infinity of f of x equals L, or limit as x goes to negative infinity of f of x equals L. We don't have to have the same limit on each side again. One of the things with horizontal asymptotes is the graph can still cross on one side. of the asymptote. Okay, so maybe only one side goes to L. Maybe they both do. Maybe one side crosses, and that's why we don't see it. For x squared over x squared plus 1, we had a horizontal asymptote at y equals 1. That's what the function went. And it was on both sides. All right. Not all graphs have horizontal asymptotes. Y equals x squared doesn't. As x goes to infinity or negative infinity, they go to infinity themselves. Negative x squared will go to negative infinity. So just because a graph, the x gets bigger or smaller, doesn't mean it's going to go to one specific number. A lot of times we see this though with rational equations, rational functions. All right, so let's look at the next one. 3x minus 1 divided by x. We'll go and plug in some values here. Some of these. Plug in 1. Plug in 10. So it goes from 2 to 2.9. We'll plug in 50. 2.98. We'll plug in 100. We'll plug in 2000. And so 2.98, 2.99, 2.9995. Right, so we can see as x goes to infinity, this function limit is going to 3. But as we input larger and larger values of x, the number is getting closer and closer to 3. Right, so that's the limit. You can see on the graph, when we zoom out, that's what it's going to. As x gets larger and larger, it's going to 3. And we see it does that on the other side too if we put a -3. Or not -3, but as x gets larger and larger, it goes to -3. Alright. So we can find these limits now algebraically. So I'm going to get this open. Alright, so to use algebra to do this, we're going to first separate the terms. So limit as x goes to infinity of 3x minus 1 over x. We'll separate the term out. Limit as x goes to infinity 3x over x minus 1 over x. And then we'll simplify, and we'll break this limit into 2. So we'll have 3 and then minus limit as x goes to infinity over x. Alright, so now a very important rule. When you have a constant in the numerator and your denominator has an x that is being raised to a power. Actually, it could just be raised to 1 power. It could just be an x. You have the variable in the denominator. The variable gets bigger, the fraction gets smaller. So, just show that real quick. If we have, let's do 1 over x. As this gets bigger, the x gets bigger, the function gets smaller. Okay, so you put in, say, 1,000,000. then you get really small. Okay. So the limit as x gets bigger in the denominator is that this is going to 0. Okay. And so we use that fact to take limits and find limits of problems algebraically. We know here the limit as x goes to infinity of 1 over x is going to go to 0. Then the limit of a constant is just the constant, so this equals 3. That's how we find the limit algebraically. Sometimes it can be harder though when you have bigger and bigger functions. Right, so limits can fail to exist first if left limit does not equal right limit. Second, the function does not approach a finite value. Third, the function oscillates. And fourth, the x value is approaching endpoint of a closed interval. So those are some basic rules for limits, and these are some laws we follow again. We went through these, sum rule, difference rule, product rule, constant multiple rule, quotient rule, power rule. Right? And so we'll be using these as we find algebraically limits going where x goes to infinity or negative infinity, and whether they equal value or not. These same rules apply for these, and that's what this is basically saying. If we have one function that's going to L as x goes to infinity or negative infinity, another function that goes to M, we can still apply these same rules, and we may be adding the limits or subtracting the limits just like we would with normal functions. And then again, as x goes to infinity or negative infinity of 1 over x to some power, these are going to go to 0. So we use kind of all these rules in tangent to solve these problems. All right, so these are all going to be x going to infinity or negative infinity, these next 4. Way we will do this is we start by dividing all terms by the highest power, so highest x to the n in the denominator. The highest power in the denominator, not the highest power overall, and all terms will be in both in the numerator and the denominator. So when I say all terms, I mean numerator and denominator. Okay. The highest power is only the one we look at in the denominator. So for this first one, highest power in the denominator is 3x squared. So we don't do the 3, but we'll divide top and bottom, all terms, by x squared. So you have a limit as x goes to infinity of 2x to the third. You're just subtracting the 2 to the power plus x squared minus 1 plus 1 over x squared. And then here you have 3 minus 5 over x plus 7 over x squared. If we're dividing this by 1 over x squared, and we're dividing both the top and bottom, we're not changing the function at all in terms of value. We're only really multiplying this by 1 still, which has always been the trick in math. So it just changes the form. Now we apply the rule as x goes to infinity or negative infinity. What happens to these fractions? So this goes to 0, this one goes to 0, and this one goes to 0. So now we have the limit as x goes to infinity of 2/3 x cubed plus 1/3 x squared minus 1/3. Okay, now at this point we have to look at each of these terms to see what happens. So x cubed, that is going to go to infinity as x goes to infinity. X squared is going to go to infinity as well. And then the minus 1/3, it's just going to slow it down a little bit, but barely any. This whole function is going to infinity. This is the same one as we just did. So we can still have the limit as x goes to negative infinity. 2/3 x cubed plus 1/3 x squared minus 1/3. But it's a little different because you have x going to negative infinity instead of infinity. You would still have done the same process. That's why I just wrote the same answer. Now we have to look at what happens when x goes to negative infinity. Well, this one's going to go to negative infinity. This one's going to go to infinity. Then you have the 1/3. However, this one goes faster because it's a cube. So the cube is going to get higher quicker than the x squared. So this function is going to negative. Alright, so let's do the next one. 2x cubed minus x squared plus x minus 1 over 5x cubed plus x squared plus x minus 5. And we're going to have this go to infinity. So same thing, divide by the highest value in the denominator. So we divide all terms by 1 over, well, we divide all terms by x cubed. We'll multiply by 1 over x cubed. We get 2 minus 1 over x plus 1 over x squared minus 1 over x cubed. And then the denominator is going to be 5 plus 1 over x plus 1 over x squared minus 5 over x cubed. All these go to 0. So this limit goes to 2 over 5. Always nice when it works out to be just a number. Then you don't have to worry about what's happening as s goes to infinity and whatnot. That always happens if the highest power is the same on both sides. And then 4x squared minus 3x plus 5 over 2x cubed plus x minus 1. We're going to divide the top and bottom by x cubed. So we'll have limit as x goes to negative infinity of 4 over x minus 3 over x squared plus 5 over x cubed. And 2 plus 1 over x squared minus 1 over x cubed. Alright, so these 3 in the top go to 0. And these 2 on the bottom go to 0. So you don't have 0 over 0. That's important. You have 0 over 2. So that's just 0. Okay. If it was 0 over 0, we actually would have a whole nother issue that we would have to take care of. We do want to check the bottom with that. Now, the functions above here, you have one function that is going to infinity, another function that goes to negative infinity as x gets bigger or gets smaller. Neither one of these two, a and b, have a horizontal asymptote. C is going to 2/5. That has a horizontal asymptote. D is going to 0. That has a horizontal asymptote. So C, the horizontal asymptote at y equals 2.5. No, sorry, I flipped that. 0.4. And D has a horizontal asymptote at y equals 0. And y's, they both have a limit L as x goes to plus or minus infinity. And we only need to show that one on one side. We can do the other side and see what happens. To see if the horizontal asymptote's on both sides. Which, if you look at it, since we didn't have to plug in anything for x, both of these will also go on both sides to that same limit. Alright, so let's keep going with this. Now, these are going to be a little different in how we go about solving these algebraically. We have the limit as x goes to infinity of x divided by square root of x squared plus 1. And so what we're going to do is we're going to, in a sense, flip this fraction. We're going to write this as limit as x goes to infinity of 1 over square root of x squared plus 1 over x. Right. And then we are going to bring that x into that square root. This may seem a little odd or counterintuitive, but this is how we would solve it. We will bring the x into the square root, so we have square root. And when you bring the x in, it becomes this x squared. So it becomes x squared because you go inside the square root. In this case, the square root, the x is not inside the square root. It's technically out in front. Here, it's inside the square root. Okay. And so now we'll split them up. You have x squared over x squared is 1, and plus 1 over x squared. This allows us now to apply the rule where if the bottom's going to infinity, your fraction goes to 0. I'll get this to be right. So this goes to 0. So we have the limit as x goes to infinity, 1 over square root of 1, which is going to be equal to 1. The same thing would happen as x goes to negative infinity. You're going to end up with the same point in the algebra because you'll do the same thing with 1 over square root of 1 plus 1 over x squared. Here's where you have to be careful though, because you have to see whether that power is positive or negative to see what happens. So, since it's even power and x is going to negative infinity, you still end up with 1 over square root of 1 equals 1. Okay. Now, just imagine if that was a cube for some reason. Now you ended up with, well, in that case, you also end up with 1. So you gotta just be careful to go through, make sure that nothing changes just because the problem changes a little bit. Alright, so next one. Limit as x goes to infinity of the cube root of 6x plus 5 over ax minus 3. Alright, so what we're going to do here is we're going to divide both of these by the cube root of x. Right, so we'll do limit as x goes to infinity of the cube root of 6x plus 5 over cube root of x and the cube root 8x minus 3 over the cube root of x. What that is going to do is going to allow us to bring an x inside the radical so we can eventually use that rule that allows us to send a fraction to 0. Right, so we'll end up with limit as x goes to infinity, the cube root of 6x over x plus 5 over x. So 6x over x is going to be 6 plus 5 over x. And then the bottom is going to be much the same way. Cube root 8x over x is 8, negative 3 over x. Right, so as these go to 0, or as these goes to infinity, it goes to 0. So we end up with the limit as x goes to infinity of the cube root of 6 over 8. Or the cube root of 6 over 2. So we use different rules for some of these depending on what allows us to cancel out some fractions and get actual value out. So you just gotta kind of be used to all the different rules you may see. Next one, imagine this as square root of x squared plus 1 minus x over 1. This is one where it's almost like rationalizing it is rationalizing the numerator. It's the one instance where we actually have a reason to rationalize the numerator. We'll multiply it by the conjugate, which in this case is going to be square root x squared plus 1 plus x. And it has to be multiplying both top and bottom. Right, so we'll work out what the limit now goes to. Limit as x to infinity. When you multiply this out, the middle terms are going to cancel. That's why you're multiplying by the conjugate. So square root of x squared plus 1 times the square root of x squared plus 1 equals x squared plus 1. And then negative x times x is a negative x squared. And then the bottom, let's just rewrite it now. Right, so the top, limit as x goes to infinity. The top, your x squares cancel, you get 1. Alright, so now we have to look at what happens as x goes to infinity. Well, inside here, this is going to infinity. And out here, this is going to infinity. Both terms going to infinity. One term goes faster. The x goes faster than the square root of x squared plus 1. Maybe slightly faster. We're not really concerned about how fast this is going to infinity. Just the fact that it's going to infinity. This goes to 1 over infinity, which goes to 0. So you limit as x goes to infinity square root of x squared plus 1 minus x goes to 0. The reason we can't plug in infinity right at the beginning is we end up with just unsure of what will happen. So, for example, this one, limit as x goes to infinity, square root of x squared plus 1 minus x. You have this going to basically square root of x minus infinity. Or square root of infinity squared, in a sense, minus infinity. We can't say for sure that it's going to go to 0. It may not. In this case, it does. In these other ones, let's do this one up top here, limit as x goes to negative infinity. You have infinity and the square root of infinity, or square root of infinity squared. It does go to 1, but we have to show it. Okay, this one over here, the cube root. This one's going to be the cube root of infinity, and this one's going to basically go to infinity as well. If you think about it, that's the cube root of 1, but that's not what it goes to. It goes to this, which is not 1. So that's why we have to go through and we have to show, does it really go to 0? Does it really go to 1? Or is it a possibility it goes to something else? All right, let's finish this out here. All right, so the notion limit as x goes to infinity of f of x equals infinity is used to indicate that the values of f of x become large as x becomes large. Similar meanings attached to the following symbols. So, limit as x goes to negative infinity of f of x equals infinity. Limit as x goes to infinity of f of x equals negative infinity. Limit as x goes to negative infinity of f of x equals negative infinity. So we can draw little graphs for these. Illustrate this graph from the top one. So going to infinity, we're looking at something like this. Exponential, for example, goes to infinity as x goes to infinity. Or it could be exponential decay, but you're looking backwards as x goes to negative infinity, it goes to infinity. Or it could be something like this. Or as x goes to infinity, it goes to negative infinity. Or as x goes to negative infinity, it goes to negative infinity. So these are different endpoints. If we look at the following limits, x goes to infinity of x to the fifth, well, this is going to go to infinity. It's going to get larger and larger and larger because x to the fifth will always increase. Okay, it's as simple as just understanding that what this function is doing, or what we had looked at before in behaviors. Let's spell it right. End behaviors. Fifth degree polynomial. It's going to have that snake curve. It's going to go off to infinity. And you see now that I drew the curve, when it's negative, it's going to go off to negative infinity as x goes to negative infinity. You can think of it as kind of plugging it in, but you can't plug it in and actually get an actual answer. For the limit as x goes to infinity of x cubed minus x squared. This is why the end behavior for polynomials always gets decided by the first term. That also is going to be like a snake. X cubed is going to go faster to infinity than x squared. So this is what's going to decide it. And so this is going to go off to infinity. Okay. Yes, the x squared is kind of holding it back some. It'll go off to infinity slower than a regular x cubed, but it does go off to infinity. And then the last one, gotta be careful of applying it directly. We still want to adjust this to make sure that we're not applying it too directly right at the beginning. If we do think about it though, this is going to be x squared minus x. So the top is going to look like it's going to go to infinity. And the bottom, well, it's a minus x, so it's going to look like it's going to negative infinity. Okay. So the question is, does it go to negative 1? Does it go to infinity? Does it go to negative infinity? Which one wins out? Or are they almost equal enough that it goes to 1? That's why we have to do the actual math here. So again, we'll divide by the highest term in the denominator. So have the limit. This goes to infinity, and we'll divide top and bottom by x. We have x minus 1 over 5 over x minus 1. And then this goes to 0. Which means we now have the limit as x goes to infinity of x minus 1 over negative 1. This is going to cause it to go to negative infinity. Okay, the negative 1 makes it become negative, but the top here is going to infinity. Because subtracting 1 from that is not going to be a huge deal. If we want to take this a step farther, if you're having trouble seeing that, you can look at the limit as x goes to infinity of x over negative 1, plus the limit as x goes to infinity of, or you have negative 1 over negative 1, which would be 1. This is just going to be 1. This again is going to be a negative infinity. So it's still going to negative infinity. It's still going to win out. That adding 1 won't change it then. And so this one goes to negative infinity. Alright. So a couple more problems. I would suggest maybe pausing the video, practicing these, seeing if you can get an answer, then come back and try them. And then you can check your answer first. If it's right, you're good. If it's wrong, look through the video and see what happens. So now with number 1, the limit as x goes to 5. If we plug in 5, we're going to be dividing by 0. But that doesn't mean there's not a limit. Okay? And I can stress that enough. Just because we get 0 on the bottom, denominator, doesn't mean there is no limit. We have to apply some rules. In this case, we're going to want to factor. And when we factor this, we get x minus 5 times x minus 2 on top. We have x minus 5 on the bottom. Well, the x minus 5's cancel out. You end up with a limit as x goes to 5 of x minus 2. That is something we can plug in. So now you get 5 minus 2, which is 3. The limit here as x goes to 5 of, I'm just going to call it f of x, equals 3. Limit as x goes to 4 of square root of x minus 2 over x minus 4. Multiply it by the top and bottom by square root of x plus 2. Don't FOIL out the bottom. We'll just leave it like it is for now. FOIL the top, but when you FOIL the top, know that the middle terms cancel. You have square root of x times square root of x is x. Negative 2 times 2 is negative 4. And this is why we don't FOIL out the bottom. You can see that the negative x minus 4 cancels. So you have limit as x goes to 4, 1 over square root of x plus 2. Now we can plug in the 4 directly. You get 1 over square root of 4 plus 2. And 2 plus 2, which is root 4. Alright, in the next video we'll look at the precise definition of a limit. It's going to be a lot of proofs. And we'll go through each one. Alright, I'll see you then.